Question 16 from Paper 2 of the 2024 Higher Physics Examinations of the SQA, the final question. A group of students use the apparatus shown to carry out an investigation into Hooke's law and find the spring constant K of a spring. There's the apparatus diagram there. You have the clamp stand, you have a spring attached to it, you have a ruler to measure the extension, and you have the masses, which of course you add on one at a time to give you the force which is pulling us down. Remember, the force is due to the weight of the springs. The spring constant K is a measure of the stiffness of a spring, and Hooke's law states that the increase in the length of a spring is proportional to the force used to stretch the spring. And there we've got the equation here, F equals KE, where F is the force used to stretch the spring, measured in newtons, K is the spring constant in the newton per metre, and E is the increase in the length of the spring in metres. Now, in our diagram here, in our results, we have measured the extension of the spring in millimetres, so we'll have to be careful of that when we work out the spring constant. So there's all our values there, 1, 2, 3, 4, 5, 6 values, and it says for 3 marks using square ruled paper, draw a graph of this. So you go to your square ruled paper and you set up the graph as follows. Along the x-axis I've put in the extension in millimetres to be 4, 8, 12, 16, 20, 24 and 28. It just means that halfway is going to be 2 and half of the halfway, a quarter way, is going to be a unit of 1 millimetre extension. In the y-axis I have got the force, and I've just used 10 small boxes to represent 1 unit of force, 1 newton, 2 newtons, 3 newtons, all the way up to the 7 newton mark. And you can see in the diagram the points that I have plotted. I have plotted those points there, and you can see that I'm getting roughly a straight line. So it's up to you to draw a best fitting straight line with your ruler. This is my attempt at it, so I go through the best fitting straight line there like that, including the origin, and I get a sort of kind of line like that. There's the best kind of line I can get, that green line. So you can see we have got a definite relationship that the force is directly proportional to the extension of the spring. Now, to find the spring constant, we have to measure the gradient of that line. And to measure the gradient of the line, we just take 2 points and construct our triangle like this. So I'm going to choose beginning of the 4 millimetres extension point and 1 newton, and then I'm going to just measure up from that, so I can just drag that down to about there. Roughly that's my triangle there. So going from 4 along the way to 20 is a change of 16 millimetres, just remember that. And 4.1 up here is a change in force, so from 1 up to this point here, 5, which is just about 5.1, so it's going to be 4.1 and 16. So to measure the gradient of that graph, just go back to the theory again. We know we're told that always told that y equals mx for a straight line through the origin, and we've been given an equation f equals k times extension e in metres. So you can see that the k value will be in fact the gradient. So we work out the gradient of that graph, we'll get the k value. So what is the gradient then? The gradient is the change in the y-axis divided by the change in the x-axis. So what's the change in the y-axis? Well, it's going to be 4.1, so we put down 4.1 and divide that by the change in the x-axis here, which is going to be 16. Now be very careful here because it's 16 and it's going to be in millimetres, so we want to change it into metres to give the correct dimensions of the spring constant. So we're going to have 16 here, and I have to multiply that by 1 times 10 to minus 3 to change it into metres. Remember, that's newton, and that now will be metres, and that's the units for the spring constant. So be very careful, that it's a kind of tricky part of this question here. So change in x-axis is 16. It's 16 millimetres. I've got to change it into metres. 16 times 10 minus 3 metres. And the change in the force one is going to be 4.1, which is going to be newtons there. So if I do that on my calculator, if I work that out, 4.1 divided by 16 times 10 to the minus 3, I'm going to get an answer of about 256 newton metres. So spring constant, 256 newton per metre. And that's going to be the value of the spring constant. So that's how you do it. Just draw a straight line. Be very careful plotting the points. Make sure you plot them accurately. Think of the scale. I've used a scale here which you can look at and work out: 4, 8, 12, 16 up to 28, and I've also used the 1, 2, 3, 4 up to 7 here newtons for that. So the spring constant becomes 256 newtons per metre. Now the second part of this question says here, suggest one improvement to the experiment procedure that the students could make to improve the accuracy of their final result. Now the final result is obviously the gradient of that graph, so to get an accurate gradient of the graph, I would need to plot more points there to get more points to see where they fit, the best fitting line fits. And that would mean by using more masses, especially in the lighter scale, lighter area down here. Find more masses that would fit into this point here. Another point is you're keeping slotting on the individual masses. If I go back up to the experimental diagram to see this, you're just putting on extra masses here, but you're taking for granted that the actual mass in grams of these masses is the true accurate one. The one thing to improve the accuracy of that experiment would be to actually measure the weight of these masses and then record that as a force, rather than just putting one on, saying 1 newton, 1 on, 2 newtons, etc., etc. You'd have to measure accurately the weight of those masses by introducing a weighing scale. Question 16, Part B. When a spring is extended, work is done. Elastic potential energy is stored in the spring. If it's not overstretched, the elastic potential energy is equal to the work done. The elastic potential energy can be determined using the relationship. So EE equals KE squared divided by 2. And we're given the definitions here. E subscript small e is the elastic potential energy in joules. K is the spring constant we just measured in newtons per metre, and E is the increase in the length of the spring, not the string, in metres. A rare mistake there from the SQA. Determine the elastic potential energy stored when the spring extension is 22 millimetres. Okay, so we've got the equation. We've got the elastic potential energy EE is going to equal to K, and it's going to be extension squared divided by 2. We know K from a previous question is going to be a value of 256 newtons per metre. That's the spring constant which we measured from the graph. The extension E at this particular point is 22 millimetres, but we have to change that into metres, so we have to multiply by 1 times 10 to minus 3 for a conversion into metres. So plug this into the equation. EE is going to equal to KE squared, so it's going to be 256 multiplied by 22 times 10 to minus 3, and we have to all square that and divide the answer by 2. So we put that into a calculator, we end up with a value of 0.062 joules. 0.062 joules is the final answer for the 2024 Higher Physics examination. I hope you did well.